This tutorial will cover the photoelectric effect. Light exhibits wave-like properties such as diffraction and interference. As a result, at the end of the 19th century, it was generally accepted that light was a wave. However, when studying the photoelectric effect, light appears to exhibit particle-like properties as well as wave-like properties. The photoelectric effect is the effect whereby when light is shone on a metal surface, electrons are given enough energy to escape from the surface. The way in which the electrons escape can be studied with this equipment. Two metal plates are arranged with one of the plates exposed to the light source. The electrons liberated from the metal travel across to the other plate, causing a current to flow. This is known as the photocurrent. The photocurrent is detected as soon as the light turns on, suggesting that light is acting as a particle. If light were a wave, the energy would build up slowly on the screen. The particles start knocking electrons off the surface as soon as the light is switched on. It was found that the photocurrent flowed when ultraviolet light was shone on the metal, but not when the red light was shone on the metal. This was observed no matter how intense the beam of red light was. This suggests that the light is made up of particles which have an energy that depends on the frequency of the light. This can be demonstrated by analogy. If you fire a high-energy photon at an electron, you will liberate it from the metal. Correspondingly, if you fire a cannonball at an elephant, you will knock it over. In the same way, no matter how many low-energy photons you fire at an electron, you will not release it from the metal. Correspondingly, you can hit ping-pong balls at an elephant as long as you want, and you will never knock it over. The energy needs to be delivered to the elephant in one go. So now we've established that light is a particle, we can study how the energy of the photon relates to the frequency. When the electron absorbs the photon, it gains all the energy of the photon. The electron then expends some energy, escaping from the metal. This energy is called the work function of the metal. The electron then has the energy of the photon, minus the work function of the material. So hence the relationship between frequency and the energy of the photon can be found through a simple experiment. If a potential difference is put between the plates using a variable power supply, then the electron not only has to escape the metal, but also traverse the potential difference in order to reach the other plate and cause a photocurrent to flow. The energy of the photon therefore needs to be larger than the work function of the metal plus the energy lost in traversing the potential difference. Otherwise, the electron cannot make it to the other plate. The energy lost by the electron in traversing the electric field is the charge of the electron times the potential difference. Hence, if the energy of the photon obeys this inequality, then a photocurrent will be detected. The photons deliver enough energy to the electrons to leave the metal and traverse the electric field. On the other hand, the voltage is increased, so the electrons don't receive enough energy to cross the gap. This inequality holds, and no photocurrent is detected. See how the electrons don't have enough energy to cross the gap. The potential difference for which the photocurrent stops is called the stopping potential and obeys this equation. If we measure the stopping potential for different frequencies, we can draw a graph of stopping potential against frequency to determine the relationship between the light frequency and the photon energy. As you can see, the stopping potential is proportional to frequency, which suggests the energy of the photon is proportional to the frequency. We can define the proportionality constant h, or Planck's constant. By relating this graph to a general linear graph, we can work out Planck's constant from the gradient. Rearranging the conservation of energy equation and expressing the photon energy as hf, we get this equation, which looks like the straight line equation. Hence, the gradient is equal to Planck's constant divided by the electronic charge. So by simply measuring the stopping potential for different colours of light and drawing a graph, we have been able to measure Planck's constant, the fundamental constant that governs the quantum world. The offset of the graph is related to the work function of the metal by this equation. These are the key points. When light shines on a metal surface, the photons deliver energy to the electrons in the metal lattice. If the energy of the photon is sufficient, the electrons receive enough energy to be released from the metal, with a little kinetic energy to spare. This spare kinetic energy can be measured. If the stopping potential is measured for different frequencies of light, we discover that E equals hf. And here are three features of the photoelectric effect that point to the quantization of light. 1. The photocurrent starts as soon as the light is switched on, so the light isn't building up wave energy on the plate over time, but delivering it as little packets to each electron right from the start. 2. Unless the light is a high enough frequency, no electrons are released, regardless of intensity. 3. For monochromatic light, the electrons all receive the same energy. That's about it for the photoelectric effect. Thanks for watching this tutorial.
Thank you for watching the video. Please like and share the video. To get more videos on chemistry, education, science career and on environment, then please subscribe my channel. Please hit the bell icon if you want to be notified for the next video. Thank you.